Oh, and this is section 5, which talks about the complex numbers. Okay, what complex numbers are, just so that you guys know, is complex numbers are numbers that have I involved in them. The complex number definition is a plus bi. Now, what the I stands for is imaginary, and what that is the square root of -1, is what that is. A is the real part, and bi is the imaginary part. Okay, and this is where we know we have answers that exist, or that we know that they are there, but we just don't know how to interpret them or how to use them other than using I. Okay, and that's where we get a square root of -1 underneath there. I itself is actually equal to the square root of -1. That is the definition of I. Now in this first little part we're going to do or talk about, we're going to have adding, subtracting, multiplying, and dividing complex numbers. And then after that we'll solve some quadratics like we learned in section 4, but with answers involving I. So first thing is that we're going to take 3 plus 5i plus 4 minus 2i. Now, a lot of times, most people end up trying to FOIL this, where they just try to do that. That's not what's happening here, because we actually have a symbol in between there. That symbol, I stole in the eraser, that symbol right there means to add. So this is nothing more than combining like terms. So 3 plus 4 is 7, and 5i plus -2i is 3i, and I'm done. Okay, so that particular thing, that's as simple as those can get with the adding and subtracting. If I subtract the two things, I end up doing the same type of scenario where I have 3 minus 4, which is -1, and I have 5i minus -2i. Two negatives make that a positive, and I end up with plus 7i. Okay? Now, typically speaking, we usually write the real part first and then the imaginary part second. However, I have seen people put that answer as 7i minus 1 because they like to see the positive in front of the negative. And that is okay because of the commutative property. We can write them that way, but typically speaking, we usually write the imaginary part first, or the real part first, and then the imaginary part second. Then if I were to have no symbol in between there, now this means multiply. When there's no symbol in between there, we're understood to be FOIL. Okay? And what FOIL stands for is first, outer, inner, last. Okay? And that's kind of the word acronym as far as how to multiply binomials together. So first being 3 times 4 is 12. Outers being 3 times -2i is -6i. Inners, which is 5i times 4, or 20i. And the last two would be 5i times -2i, which is -10i squared. Now, when I just gave you a few minutes ago that I was equal to the square root of -1, if I square both sides, I end up with I squared equals, well, when you square root a square or vice versa, you get the inside material. So this here is really saying -10 times -1. And two negatives, when you multiply them, give me a positive. So I end up with 12 minus 6i plus 20i plus 10. And then I combine like terms. 12 plus 10 is 22. -6 plus 20 is 14i. And I now have my part. You should not have anything that has something greater than I squared. It should only be I, because if you do have something bigger than that, it will reduce. Before we get into the dividing, let's go through this a little bit more with I. I itself will equal I, but I squared, as we just showed, equaled -1. But what happens when you take and find I to the third? Well, I to the third is really the same as I squared times I, because when you add exponents, you should get 1 plus 2 is 3. Well, I squared was -1, and I was still I, so that ends up being -I. That's what I to the third is. I to the fourth is really like saying I squared times I squared, or negative 1 times negative 1. And when you multiply two negatives together, you get a positive. So right now, these are the answers that I'm getting. And notice, no I has a higher exponent than 1. If I continue the pattern, I to the fifth is the same as 4 and a 1. Well, 4 was 1 and I was I, so that's 1 times I, or I to the sixth is the same as a 4 and a 2. That's negative 1 times 1, or negative 1. I to the seventh is the same as a 6 and a 1, which would be negative I. I to the eighth would be a 7 and a 1, or a 6 and a 2, or whatever, and I still get a positive 1. And what I'm trying to get at is that this right here is repeating a pattern. We have the same numbers over and over again. So if I were to give you something very high, like I to the 1,000, for instance, I to the 1,000, I'm not going to write out every number all the way to 1,000 just to get that. What I am looking at is, and if I hope you notice this, is that these are in multiples of 4, where the fourth one is 1, all the other evens are negative 1, and then after that we'll go from there for the i's. But the first thing I do is I take this exponent and I try to divide it by 4. If it divides equally by 4, then it's the same as this one here, if it's an even number. If it's not divisible by 4 and it's an even, then it's equal to the other one. This one here, 1,000, can divide by 4, so therefore it's the same as 1. But what if I gave you 423, for instance? That's not even, it's odd. So if you look at the odd exponents, you're either going to have 1, or I, or negative I. So it's up to us to figure out which one it is. So what I do is I add 1 to it. Oops, that's not what I wanted to write. I add 1 to the exponent, and I see if that's divisible by 4. If it is, which 424 is, then that would be the same as 1. And according to the pattern, 423 would be the one previous to 1, which is negative I. So that's how those ones kind of work out, where you're looking at how are they related back to that multiples of 4. From there, we're now going to divide. And dividing, in order to get rid of this, now a lot of people, when they look at it and go, well, I is in the bottom, big deal. Well, it is a big deal because it is the square root. I, again, is the square root of negative 1. And you're not allowed to leave square roots in denominators of fractions. So therefore, what you have to do is you have to multiply by its conjugate. Now the conjugate of the bottom is 1 plus 2i. So if you notice, what I did is that I changed the middle sign. That's what I did. And what you do to the top or bottom, you got to do to the top, and vice versa. For this particular thing now, it turned into 2 multiplication problems. One on the top, one on the bottom. Me personally, I like to start with the bottom. However, it does not matter. Again, this is nothing more than FOIL. 1 times 1 is 1. 1 times 2i is 2i. Negative 2i times 1 is negative 2i. And negative 2i times positive 2i is negative 4i squared. Now, one thing that I hope you notice is that these two I pieces here will cancel. When you multiply conjugates together, regardless of if it's I or not, if you multiply conjugates together, the middle two pieces of FOIL will always cancel each other out. So therefore that goes away. This, remember, is the same as negative 1. 2 negatives make it a positive, and I end up with 1 plus 4. And so my bottom ends up being a nice number. It does not cancel everything out. That's one misconception with it, is that people think that it's just going to cancel the whole thing out, but it's just the middle pieces, or just the i's, that will be gone. Now it's time to do the top. What's 3 times 1? 3. 3 times 2i is 6i. 5i times 1 is 5i. And 5i times 2i is 10i squared. But again, I squared is negative 1. So that ends up being 3 plus 6i plus 5i minus 10. So what happens is as soon as you see this I squared, it basically just changes the sign that's in front of it. And then we combine like terms. 3 minus 10 is negative 7. 6 plus 5 is 11i. And now it's very similar to the quadratic stuff where if I can reduce all three pieces, go ahead and do it. You cannot do one versus the other. So for example, if that would have been negative 10 plus, not plus or minus in this case, but just plus 11i over 5. If you split it into two separate equations, you can go ahead, but you cannot just simply reduce that and not the 11. So if you put negative 2 plus 11i over 5, or over 1, that's not right. Okay? You can't just simply do these two and not this one. I kind of steal a quote from like the Three Musketeers in this case, where it's all for one and one for all. And that's how we do that. We do not do it where it's just one versus the other. Okay? Then, along the same kind of concept, if we have the square root of 12 minus the square root of negative 3, and 3 plus the square root of negative 4, we can do this one of two ways. We can take the i's out first, or we can take the i's out afterwards. It does not matter. Me personally, I like to do it afterwards. So this is still FOIL. When you have a inside piece with an outside piece, the outside multiplies with the outside, and the insides multiply with the insides. So I end up with 3 root 12. Then when I multiply here, the insides multiply together, and I get plus the square root of negative 48. Then again, when I multiply here, that's an outside number. Oops. That should have been negative. And then an inside number. And then here, I would have had negative the square root of 12. And I hope you notice that what happened there is that I had negative 3 times negative 4, so I get positive 12. Now, when you're adding and subtracting square roots, you can do it if the houses or the square root is exactly the same. If it's not the same, you cannot do it. So in this case, I have 2 root 12 plus the square root of negative 48 minus 3 the square root of negative 3. Now that is a little bit sloppy because the square roots are not reduced. When you reduce square roots, I like to do a little technique I like to call upside down division. And what I'm doing is that I am just walking through a prime factorization type thing. The reason why I do this is now if it's square root, I can take out a pair of 2's. This 2 and this 2 multiply each other together to give you 4, and then the whatever left over stays inside the house. I'm going to do the same thing with the next 2, but the next 2 have I pieces. If you have a negative underneath the square root, you need to take the I out. So if I have 48, that's really going to be plus I the square root of 48, and the I is going to have to stay there. 2 goes into 48 24 times, 2 goes in there 12 times, 2 goes in there 6 times, 2 goes in there 3 times, and 3 goes in there once. I got one pair of 2's, another pair of 2's. 2 times 2 is 4. I the square root of 3. Now this one and this one cannot combine together because one has an I and one doesn't. So be very careful with that. With the square root of 3, this one had to take the I out. So minus 3I root 3. Now as long as the I root 3's are the same, like they are right here and right here, now I can combine those together though. So I end up with 4 the square root of 3 plus I the square root of 3. And that would be my final answer. A lot of people then end up trying to get, they try to reduce that or do whatever they need to do for that, but it doesn't always work when you with the I and without it. Okay? And the last thing that's involved in this is what happens when I have a quadratic where I know I'm going to have an I. So if I have x squared plus 4x plus 5. A lot of times people think, oh, I can factor that. But remember, when you factor it, it needs to remultiply back out to be the original. And no matter what you write, it's never going to make a positive 4 and a positive 5. So therefore, I'm going to use the quadratic equation. So since it was equal to 0, 4 is going in the b's position. Minus 4 times the a times the c. All over 2 times the a. Negative 4 on the outside. And then 4 squared is 16. Minus 20 over 2. Negative 4 plus or minus the square root of negative 4 over 2. As soon as you see a negative underneath there, what you have to do in order to solve this is you have to take an I out. If you don't take the I out, it doesn't actually work. I is an imaginary solution. This parabola would actually have a parabola that opens up, but it does not actually cross the x-axis. So there is no real answer for this, but there is an answer. And then from here, the square root of 4 is 2. And then I reduce all for 1 and 1 for all. Negative 4 can divide by 2, and 2 divided by 2, so I have negative 2 plus or minus I. And that would be my final answer. So that is very similar to what we did in the last section. They're going to ask you to express it in the form of a plus bi, which is what we just did there. So with that, if you look at the directions, for 1-5 it says find the real and imaginary parts, which you just have to identify them. Sum and difference means add or subtract. Product means to multiply. Quotient means that you're going to multiply by the conjugate. Evaluate the powers, that's where I did that I to the 1,000. Multiplying by negative, or multiplying by conjugates. And then finding solutions of the equation. The difference with this type of thing is compared to section 4. Section 4 said find all the real solutions. This one says find all the solutions. If they don't specify, it's always find the solutions, which means you can have I's. Okay, so with that said, that's it for section 5. Thanks.